below the curve from A to X. So A here is some fixed left border, and you're sliding X back and forth. X is now the variable, and you consider the area. That's a function of X. Call that g of X. If we define g of X that way, then in fact the derivative of g at X is the same as F. So g is accumulating this area. The rate of change of that area accumulation is actually equal to the value of F right at that point. So that's one way of saying, that's one way of expressing the fundamental theorem of calculus. Here's the other way. If you take a function f and take its derivative and integrate the derivative from a to b, then that is just equal to f of b minus f of a. So here, you take something, differentiate it first, and then take the integral. It gives you something like the function back again, in some sense. Where here, this is the opposite. If you take a function and integrate it, and then differentiate the result, you get back the function. So these two are inverse processes. That's what the fundamental theorem of calculus says. Yeah, we can ignore this slide. I don't think it's important. Well, maybe it's important. You can set one or both limits to minus infinity or to plus infinity, and that just means take the area under the curve all the way. There's no bound. There's no lower limit, or there's no upper limit. Just take it all the way. And A doesn't have to be less than or equal to B, because if I flip the borders, then I negate the integral. So this is the integral from A to B, but you can also consider the integral from B back to A. By convention, that's the negation of the integral from A to B. So if you flip the direction, you negate the integral. What essentially you're doing is you're turning the delta x from a positive increment into a negative increment, and that's what does it. All right, enough of that. So that was a little more than a minute. But now we can talk about continuous random variables. So, for continuous probability distributions, the thing about a continuous distribution is that it doesn't make sense anymore to consider the event that a continuous random variable is exactly equal to a particular value. That's always going to, the probability of that is always 0. Like if you're the number of inches of rainfall, the chances that the number of inches of rainfall you're going to get is exactly 3 inches. It's never going to happen. It's always going to be off a little bit. So the probability of being exactly equal to a value is now 0 for all x, so it doesn't even make sense to actually ask the question, what is this? Instead, we can ask, what is the probability that a continuous random variable is in a certain range, in a certain interval between one thing and another? This is what we can ask, and this is how we actually define the probability function, or the probability characteristics of a continuous variable. We do that by doing the cumulative distribution function. So here's what we can do. We can ask, for any value x, what's the probability that the variable is less than or equal to x? And when we do that, we're going to get a particular probability. And as x increases, this probability should get larger, right? Okay. We can often express that as an integral. An integral for some other function, little f of t, from minus infinity up to x. So remember, in the discrete case, the cumulative function of x was the sum over all the possible values y less than or equal to x of the probability of y. Well, here, we're taking some function of t less than x, and instead of taking its sum, we're taking its integral from minus infinity up to x. This f of t this little f of t is called the probability density of the function at a particular point. The probability density says if I have a small interval around the point t, with width, some small width, what is the probability of the random variable being in that interval? And it's going to be proportional to the width of the interval. But basically, that constant of proportionality is called the density, the probability density of the function. So you take the density, multiply it by the width of that tiny interval, and integrate that all the way across. So this gives you the continuous version of the cumulative function. Here, its properties are similar. So the probability density always has to be at least 0. If you integrate this over all possible values, minus infinity to plus infinity, then you get probability 1. Okay, because the random variable is always going to be somewhere there. So these are value restrictions. These are normality restrictions. So that's for the probability density. For the CDF, the cumulative function, the value restriction is always between 0 and 1 because it's a probability. If x is less than or equal to y, then f of x is less than or equal to f of y. So as x increases, this thing has to increase. That's called monotonicity. F is monotone. And finally, the normality conditions is if we take the limit of this thing, as x goes to minus infinity, we should get 0. So the probabilities go diminish to 0. And if we take the limit as x goes to plus infinity, we get 1. We have formulas now for the expected value and for the variance of a continuous random variable. And again, sums turn into intervals when we go from discrete to continuous. So the expected value now, instead of taking a sum over all possible values, we integrate over all possible values of the random variable of the value x times its probability density. And we just integrate that over the entire real line, and that gives us the expected value. The variance can be expressed strictly just in terms of the expected values of these random variables. So we could do it this way, for example. So that's going to equal this minus that. That's one way of doing it. But now it's just that this is the same as the discrete case, except now sums are now intervals. And the probability function is now a probability density, which you integrate rather than summing. All right. So here's some more contrast. Here is a discrete random variable. This is a 3-coin toss. This is the probability function. Or you can take a Gaussian distribution. This is a bell curve. This is a continuous random variable, continuously distributed random variable. And here's its density function. It's the blue line. Density function tends to vary continuously, whereas in the discrete case, I just have a discrete set of values. The cumulative function in the discrete case looks like it's called a step function. It's constant for a while until it gets to the first value, and then it jumps up. And it's constant for a while, and then it jumps up like this. So it jumps up stepwise. It's constant except for some discrete jumps that it makes. In the continuous case, the cumulative distribution tends to rise continuously. As x gets bigger, this thing just tends to climb continuously, rather than in these jerky steps. Okay, so here's a cumulative random distribution function of the Gaussian. All right. Great. So that ends the general discussion. I know people just looked at the clock to see, is it break time? No, we gotta keep going. That ends the general discussion of probability distributions in general. Now we're going to get to those 4 special ones, and we're going to talk about each one in detail and describe how it arises and what it's used for. Two of them the first two are discrete, and the other two are continuous. So the discrete ones we're going to do are the binomial distribution and the Poisson distribution. These are probability distributions for collections of random variables that often occur in the real world. Okay? And they have probabilities according to a particular distribution, and here's how we're going to describe them. All right, so a binomial experiment is characterized by the following properties. So this is a type of random experiment. The random experiment consists of n identical trials. Each trial results in two possible outcomes, say success, denoted by S, or failure, denoted by F. This is called a Bernoulli trial. So a trial that has two outcomes, and we just arbitrarily label them success or failure, but we can label them other things. We call it a Bernoulli trial. A binomial experiment is n identical Bernoulli trials. The probability of success on a single trial is p, and it remains the same from trial to trial. So the failure probability then, since there are only two outcomes, the failure probability we call q, that's just 1 minus p. The trials are independent of each other. So no outcome of one trial affects the outcomes of any other trial. And the random variable we are interested in for a binomial experiment is the number of successes observed during the n trials. So this is going to be a discrete random variable, right, because it's a whole number. What are the possible values? 0, 1, 2, up through what? Up through n. Yeah. So there are n trials, so there can be at most n successes, or there could be 0 successes, or any number in between. Okay. So now what we're interested in is what is the probability, given a particular number of successes, what is the probability of getting exactly that many successes and the rest being failures? That is the binomial distribution. So, is the 3 coin toss experiment a binomial experiment? It is. Assuming you toss the same coin 3 times. Okay? If it's a fair coin, then it's still a binomial experiment. But the coin doesn't have to be fair. So, yes, 3 identical trials. Trial results in success or failure. The probability of success remains the same from trial to trial, and in fact, if it's a fair coin, that probability is 1/2. Each coin toss is independent of the others, and we're interested in the number of heads. So in this case, we consider heads to be success and tails to be failure. So the number of heads in a 3 coin toss experiment, that is the random variable of interest. All right. So in this case, we have 2 parameters that we set, 2 independent parameters that we set for each binomial experiment. N is the number of trials. In this case, it's 3. And P is the success probability. In this case, it's 1/2. And then Q is just 1 minus P. So that's dependent on the other 2. All right. So in order to figure out the probability of exactly K successes in N trials, we introduced more math notation called binomial coefficient. So part of this formula is going to be a binomial coefficient. A binomial coefficient is, think of this as just a binary operation on integers. If I take 2 integers, n and k, here, n, eventually n is going to be the number of trials, and k is going to be the number of successes that we're interested in. This value, we're going to define it to be n factorial divided by k factorial times n minus k factorial. We all know what a factorial is, right?
No.
Nope. Okay. N factorial is just the product of all integers, from 1 to n. 0 factorial is defined to be 1 by convention. And then 1 factorial is 2. 2 factorial is 2 times 1. I'm sorry, 1 factorial. 2 factorial is 2 times 1 is 2. 3 factorial is 3 times 2 times 1, which is 6, and so forth. 4 factorial is 24. And in general, n factorial is n times n minus 1 factorial. Because this is the product of numbers up to n minus 1, and then to get n factorial, you just add one more factor in. And this is it. That's the factorial function. It pops up a lot in calculus. You might have seen it in, Taylor series. See it there. You see it in a couple other different places. And it pops up here. So the binomial coefficient of two numbers here, and here we're assuming that k is some integer between 0 and n. So k has to be in the range 0 to n. And we read this as n choose k. There's a significance to this number. N choose k, if I take n things, n choose k is the number of ways of selecting k things out of those n things. That's why it's called choose. It's the number of different ways that you can choose a subset of k things out of a set of n things. Okay. You can calculate these numbers actually fairly quickly. You can plug in the factorials, but sometimes the factorials get kind of large. For small values of n and k, you can build a table of binomial coefficients very quickly. This is called Pascal's triangle. So each row, the rows are indexed by n, and the columns are indexed by k. And we assume that k is between 0 and n, so this part of the table is just blank. So it's just this triangle here. And here's how you get the entries of the triangle. Well, you have 1s along the 0 column. So n choose 0 is always 1. Is always equal to 1. Okay, that's easy to just plug that in to the formula. Likewise, n choose n is always equal to 1. So you've got 1s going down that column. You've got 1s going down the main diagonal because of that. Then how do you get all the other numbers? Well, to get any number here, you take the two numbers above it, the one above it, directly above it, and the one just to the left, and then you add them. So, for example, 20 is 10 plus 10. Oops. And so, for example, 21 is 15 plus 6. So you can get all the entries in the table very quickly just by adding the two above. And you do that everywhere, and you get this. Now, the other thing to notice, as you go across, if you pick n constant and k increases from 0 to n, the numbers change, but then they start reversing. So in fact, if you read these numbers backwards, you'll get the same sequence. So this is symmetric up to reversal. Okay, that's true for every row. So in math, that is n choose k is equal to n choose n minus k. That's the reflection in the row. That's also true. That's just some basic properties. All right. So given Pascal's triangle, given binomial coefficients, now we can define the binomial probability distribution. So, the binomial probability distribution is as follows. It will give, given a particular k in the range 0 through n, it will give the probability of exactly k successes in n trials. And it's notated by this convention. This is b of k given parameters n and p. P is the success probability. It's n choose k times p to the k times 1 minus p to the n minus k. And this is true for all k from 0 to n. So if we fix n and we fix p, and we let k vary from 0 to n, we take these numbers. These are probabilities. It's a probability distribution on the number of possible successes. So if you actually add up all these probabilities, you're going to get 1. So k is the number of successes in n trials. P is the probability of success in an individual trial. So let's do an example, because examples are much easier to learn from. So consider you toss 20 unfair coins, or biased coins, where the probability of tossing a head in a single toss is 0.8. So 8/10, or 4/5. What is the probability that you get, say, 5 heads out of 20 tosses, or 10 heads, or 15 heads, or 20 heads? So what are these 4 probabilities? What is the probability that at least 15 heads are tossed? Plot the probability function and the distribution function for this experiment. Okay. So this is a lot of coin tosses. This is 20 coin tosses. Well, here's the probability of getting 5 heads exactly. Plug that into the formula here. Here, now, n is what? It's the number of trials. So what is n in this case? 20. Good. What's p? It's 0.8. Okay, because the coin is biased. All right. So what is k for this first? If we're probability of we're getting 5 heads, that means k is 5. Number of heads is equal to 5. So we just plug those numbers in. We get 20 choose 5. So 20 factorial over this thing. 5 factorial times 20 minus 5, so that's 15 factorial. Times p to the power of k, so that's 0.8 to the 5th, times 1 minus p, which is 0.2, to the n minus k, that's 20 minus 5, so that's 0.2 to the 15. Plug that all in, and it is approximately equal to 1.66 times 10 to the minus 7th. So this is less than 1 in a million. So this is very small. Okay. Probability of getting 10 tosses, the only thing that changes here is k. K is now 10. Plugging that up here, you get 0.002. 15 tosses, you get 0.175. Now this is actually fairly likely. This is close. This is actually significant. You'd see this if you did this. If you did this whole experiment, a few times, you'd actually see this occurring probably. And the probability of getting 20 heads is now going down again. It's 0.012. So this is the biggest number of these 4. There's a reason for that. The chances are going to be greatest that you get a number of heads equal to the expected number of heads you get. You're going to expect to get about 0.8, 8/10 of, so that's going to be 16 out of 20. You expect to get 16 heads on average. Anything close to 16, that probability is going to be fairly large. The further away you get from 16, it diminishes very quickly. All right, we're almost done. So here is the probability function. So for each k, here is the probability of getting exactly that many heads as k goes from 0 to 20. you know, it's almost 0. It's indistinguishable from 0 until you get just a little bit past 10, and now it's climbing up, and now it reaches its peak at 16, which is the expected value number of heads, and then it goes down again. Now, the cumulative function is what you get by adding all of these, adding everything together at the point and to its left. And so the cumulative function is going to be increasing most steeply right here, where you're adding the most stuff each time. And so it's going to go from 0 and increase, and it'll eventually end up at 1, because you add them all together and you get 1. Okay, here's a table of the actual probabilities for getting exactly k heads, and this is getting at most k heads. So the probability that you get exactly 15 heads, well, we did that using the formula, but if we have the cumulative distribution, there's another way of doing that. This is, you get exactly 15 heads if, just in case you get at most 15 heads, but you don't get at most 14 heads. So this is the relative complement of getting at most 15, but getting strictly more than 14. So you take the probability of getting 15 heads and you subtract off that sub-event that says you're getting at most 14, and what's left over is the event that you get exactly 15. And so these two numbers, you subtract them, and you get the probability of exactly 15 heads, and you can just subtract these entries in the table. That thing minus that thing gives you 0.174, which is what we got before. Close to what we got before. Questions on that? Okay. Just a promise, take a break in just a second. I want to get through this. Binomial probability, so nothing more technical now. The mean of a binomial distribution is just the number of trials times the success probability. So you take the probability of success per trial, multiply that by the number of trials, that's the expected number of successes you're going to get. So in the case of 20 coin flips with a 0.8 probability of success, it's going to be 0.8 times 20, which is 16. That's almost intuitively true. Okay. The variance, this is also interesting, the variance is the number of trials times the success probability times the failure probability. So, a little bit different. But there it is. Okay. Why that's true, you don't have to know that. It's just a nice simple formula you can plug in and do it. So in our case, NP, the expected number, is 16 heads out of 20 possible. The variance is going to be 20 times 0.8 times 0.2. That's 3.2. Standard deviation is the square root of that. So standard deviation is about 1.79. That tells you the dispersal. What's that curve look like to you? Looks like a bell curve. And in fact, it is approximately a bell curve. So, all right, let's take a break. I'll give you a 10, just because it's nice. And I'll get some more coffee.
Long day.
A long day, yeah. This is a long day. No question.
It started off long.
Yes. Short night last night, long day today for me.
Yeah, we'll find out when we get the homework.
Yeah.
Oh, I think I got it. Hey, my weekend. There it went. I'll see it. Great weekend. Last night's game? No.
The soccer
So it's 10.
10, 23, 13.
Drew Brees did not throw a touchdown for the first time in
Like
3.5 years. Got 5 picks, actually 6, but the one got negated by the flag.
Wow. I really don't want the Rams to lose. They're like the most overrated.
I think they are. When Arizona comes, so he's going to be.
Yeah.
And you guess
Yeah. They're overrated.
I really think that Arizona game showed that I think that Arizona
Yeah.
You just have to be aggressive on defense.
Yeah, but
Start throwing in trouble.
yeah. I think it's going to be Houston and Baltimore in the AFC Championship. Not sure about the NFC. I don't know what the thoughts are going to be.
I think the NFC is more evenly matched this year than the AFC.
Yeah.
The AFC, like Houston's really dominant, and the Ravens are clearly. There's not a lot of other good teams in the NFC.
The Super Bowl champion will be in the AFC.
You mentioned that it's like none of us will wait for
That's it. Alabama's going to
At least you should.
throw to that.
Think so?
Oh, yeah.
This FA24
Graduating 4 versus 4 that can come to the last.
Alabama won last year. Here's my thing. I don't personally care who wins. They better not screw up and not win the BCS.
Yeah.
Because that's worse.
Notre Dame is pretty good.
Yeah, but I
They
think
cannot do so.
That's the thing is, I think Notre Dame's defense can play with Alabama's offense.
Yeah.
I don't think Notre Dame's offense can do shit against Alabama.
No, that's going to be
I think it's
bad.
going to be like a 9-6 game.
yeah, I see it. Yeah.
I think,
It'll be interesting. Part of me kind of, I mean, and I shudder saying this because I'm not a Georgia fan by any means. I'm a Florida fan, so like, part of me kind of wants Georgia to win. I mean, Alabama won last year.
Yeah.
Part of me kind of wants Georgia because they haven't won in like who knows when. And they actually seem to have
6
a
years.
really good team. 6 years. Yeah. So they actually have a really good team this year.
can we do a probability problem on,
I don't know. Could you do that?
I still want to get it wrong because none of this is
If you
fixed.
show word and you get the wrong answer, you can say partial credit. If you don't show word and you get the right answer, you get all the credit. If you get the wrong answer, you get nothing.
The calculator does have published. And I checked that I plugged it in and was getting the same answers.
So if you fat finger something, though,
Yeah, that's the question. So it's this because you know it was the $145 investment, which is the probability of you passing the exam is significantly rise. We're allowed to do that. That's how everybody sees some sort of
you just see the calculator, you need this do any sort of signal.
That's all I was going to say. I'm not.
Yeah.
Yeah. I was getting my MBA. I go one work and I had to doing no line.
I think I know how we're going to play this. We're going to capture the hits and that's it. Yeah. I can't figure out how to play this. Capture all the text. All about, No, I think major talent.
What's up?
I think major talent.
Whoever's got the off button, can we hit it back on?
I looked at that back for
Actually, well, I can't say that because a lot of that stuff he's used later on was like, is this just like a Yeah. Or is this just some of it to just kind of sit there and go, who really wants it?
Not bad, maybe so.
Are you really?
A lot has to do with this, but it has to do with our
Yeah, I never actually had a question for real G after selection.
No, I'll admit, if you find yourself in a war zone, it's good to know you don't have to react to that situation.
I was straight. Stuff like that, you know, and I'm thinking, like, who's going through all this?
But 2 months of work food.
Yeah, but you never know, like,
like without Morse code, they like in their body. It's not that smart.
Figure out what you get.
God knows.
It's different. And I got another one last night. You wouldn't be torture. Maybe. No, maybe. We got the red potato pie.
It's on gate 2?
What's that?
It's on gate 2?
Yeah.
Just hang a right and do a U on Gordon Highway. It's quicker because that lane to turn right.
No, I'm talking about like going through Grovetown. Like if you live in Grovetown, there was an accident yesterday when I was coming back with the pizza or whatever like that. And it was just like that one lane was stopped. It's like, it's a 2-lane road. And
Oh, yeah. That's it. All right, so let's go. So you've drunk your monsters, and well, just one more hour to go, and we're done. So, all right. So enough of the binomial distribution. Next, we come to the Poisson distribution, which is the other discrete distribution we're going to talk about. So here we have the experiment in question is similar to the binomial experiment, but instead you're going to be interested in the number of successes, not in some fixed number of trials, but in some finite period of time, or finite volume, or finite area, and so sort of some finite region. And here, instead of having some discrete finite number of trials, a success can come at any point in time, or can appear anywhere in the area, okay, independent of what else happens. So, examples. Number of phone calls the call center gets in any minute. So here the interval of time is some specific minute. And the point is a call can come in at any time. There's no discrete point where a call can come in absolutely any time during that minute. Spelling mistakes the secretary makes on the page. So if you think of the page as the number of letters on the page is big enough that you can think of it as being a continuous stream of text, a mistake could come absolutely anywhere on the page. The number of times a web server is accessed in a given minute. So an access will count an access as a success, or before a mistake is considered a success, even though it's not really. So a web server is accessed, the number of times a web server is accessed in a given minute. So the number of occurrences of something in a given unit of time or space. Roadkill found on a given length of road, so the number of actual roadkills you found in the, like say, in the next 5 miles of road. All of these are going to be Poisson distributed. So we have to understand what that distribution is. Pine trees in a given square mile of forest. This is also Poisson distributed. Stars in a given volume of space. Point is, anywhere in the forest there could be a pine tree. Anywhere along the road there could be roadkill. Anywhere in a volume of space there could be a star or not. Requests in a single second on a file server, or requests to be come in at absolutely any time in that second. Data packets arriving at a router in a given millisecond. In this case, we're always counting the number. The number of data packets arriving at a router at a given millisecond. Errors that occur during the transmission of a fixed length message, or an error could occur anywhere. These are all Poisson distributed. So, in order to determine what these probabilities are, we have to choose some parameter. And the parameter is going to be lambda. This is the average number of successes. So we always imagine that there's some average number of successes we're going to expect in the interval in question, in the minute or the second or the volume of space. There's some expected number. We'll call that number lambda. K is the actual number of successes we desire in a time period. And E here is just the usual constant. This is the base of the natural logarithm. Okay. So what the Poisson distribution says is that the probability of exactly K successes in the time interval is lambda to the K times E to the minus lambda, all divided by K factorial. And this is K can be 0, 1, 2, 3. It could be any number. There's no bound. There's no finite bound on the number of successes you could have in this time interval. Okay. So this is an infinite distribution, a distribution for infinitely many possible values of K. This gives you the probability of finding exactly K occurrences in the interval in question. Given that we know the average number of occurrences. And an occurrence can come at any point, and whether or not occurrence occurs at some point is independent of the past history, whether occurrences occurred earlier or later. Okay. Calls coming in just come in independent of other calls coming in. This is a call center. So the mean of a Poisson probability distribution is mu. It turns out to be equal to lambda. Well, that almost goes without saying because we already said lambda is the average number of successes we expect. So we'd expect the mean of this distribution to actually be equal to lambda, and it is. You can verify this mathematically. The variance of this distribution is also lambda, actually. So this is very interesting because the variance now, remember, the variance is usually in different units in the mean. Well, here, there's no units. These are just numbers of events. But the fact that the variance and the mean are equal is kind of surprising, and this actually, you can use this fact to determine lots of things. Okay, and there's a question on the homework I'm going to hand you that actually uses this fact to actually determine something that you would not otherwise be able to measure directly. it determines granularity. All right. But let's set that aside. So let's do an example. So consider a file server on the network. Assume that requests for service are Poisson distributed, so the number of requests in any given time interval is going to be Poisson distributed, with an average of one request every 0.25 seconds. So on average, one request comes in every quarter second. So yeah, that's 4 requests per second. Yeah.
That's what I'm throwing off on this reading that. So that's what we're considering to be a success is 4 requests per second.
That's the average number of successes. So a success here is the same as a request.
Okay.
So think of a request as a success. Then the average number of successes per second is 4. Okay, if a request comes in every 0.25 seconds. So let's find the probability of getting 0 requests, 1 request, respectively, up to 5 in a given second. So there are going to be 6 different answers here, 1 for each value. Also, find the probability of at least 3 requests in a given second. Plot the probability distribution and the distribution function for this problem. Also determine the mean and variance of the distribution. Okay, so the one parameter we need is the average number of successes in the time interval in question, which happens to be 1 second here. So what's lambda? I've already said it. It's 4. Yeah, so lambda is 4. So lambda is 1 request every 25 seconds, 4 requests per second. We're dealing with, that is our time interval. That's our designated time interval. So the answer for lambda is 4. 4 is, it's just the bare 4. There's no units. Okay. Now, if we were worried about the number of successes in a minute, then you'd have to convert lambda into successes per minute, which would be 4 times 60. So that would give you an entirely different value of lambda, because it's a much longer time interval. Okay, but here for 1 second, lambda is equal to 4. So let R be the random variable that is the number of requests in a 1 second interval. Then the probability of getting exactly 0 requests, 1 request, 2, and so forth, we just plug that value of k into the formula we had up before. So it's going to be lambda, k is 0, lambda to the 0 times e to the minus lambda over 0 factorial. What's 0 factorial?
1.
1? Good. 4 to the 0 is what?
1.
1. Good. So all of this is just e to the minus 4, which is about 0.0183. Probably getting exactly 1 success is 4 to the first times e to the minus 4 over 1 factorial. What's 1 factorial? 1. What's 4 to the 1? 4. Okay. So this is going to be exactly 4 times that. And it looks like it is. Exactly 2 requests, no more, no less. 4 squared, e to the minus 4 divided by 2 factorial. 2 factorial is what? 2. Okay. That, and so on and so on. So these numbers start out fairly small, but then they increase, and they reach their peak right around here. They're actually equal in this case. That peak occurs right at the average number. So again, the peak, the highest probability, is right at the expected number of requests for that time interval. In this case, 4. So when k is equal to lambda, that's where the peak is. All right. Here is a plot. So if we plot the probabilities for exactly k requests, as k goes from 0 on up forever, we'll just cut it off at 20. We get this thing, which kind of looks like a bell curve. Not quite, but kind of. It's a hump, definitely. And it drops off exponentially, for sure, as k increases. As k gets really large, compared to the average, the probability really is so close to 0, it's practically never happens. And here, again, is the cumulative function. Here are the tables of values we get for each. And notice probabilities are going down very quickly. These are very tiny. These are less than 1 in a million. This is close to 1 in a billion. And here's the cumulative distribution. And by the time we get up here, it's so close to 1, it's really indistinguishable from 1. It's very, very close to 1. So it's almost, with almost certainty, you will get no more than 20 requests in a given second if the average is 4. Okay. Questions on the Poisson distribution? What is the probability of getting at least 3 requests? So this is useful to know. What is the probability of getting at least 3 requests? Well, at least 3 requests. Now we got to use complementarity. The event that you get at least 3 requests, what's the complement of that? That you get. The complement is that you don't get at least 3 requests. In other words, you get less than 3 requests. So the complement of the event that you get at least 3 is that you get less than 3.
So you do the cumulative for 2?
Yes, exactly right. So the point is, if you get less than 3, that's the same thing as getting at most 2, right? Because you only get an integer number of events. So the probability of getting at least 3 is going to be 1 minus the cumulative function at 2, which is the probability of getting at most 2. You take 1 minus that because it's a complement. And so f of 2, you go up here, f of 2 is 0.2381. Subtract that from 1, you get 0.7619. So you can play tricks like this with the cumulative function to get, say, probabilities of being greater than something, or less than something, or less than or equal, or greater than or equal, or even in some range where, greater than this number but less than or equal to that number. You take the cumulative function here and subtract off the cumulative function there. And you get the difference is the probability of the range. So you can play tricks like this to get these things. Questions? All right. So finally, 2 continuous distributions, and then we're done for the day. And the first one, the exponential distribution, is nice because it arises from exactly the same setup that we use for the Poisson distribution. So in a process, we'll call these processes Poisson process. So Poisson process is what led to the Poisson distribution. We think of successes as coming in at any point in some interval. And but we have some average number of successes in that interval. So the same setup, the same parameter lambda, same interval, but now we're interested in a different quantity. So we're interested in the waiting time until the first arrival comes, or until the first success. So this is, you've got calls coming into the call center, and you start your stopwatch at some point. And you want to ask, what's the probability that the next call is going to come in, say, within the next 2 seconds? Okay, from now. That gives you a random variable. Actually, that gives you a probability. The probability depends on the time that you wait. So it's continuous, because it depends. So the time could be any real number. Okay, the waiting time could be any real number. So it's a function of the waiting time. So it's the waiting time until the first arrival, success, request, whatever. And this is exponentially distributed. What that means is, well, its density function looks like an exponential. Don't worry about the density function too much. Worry about the cumulative distribution function. That's the most important. The probability that the next success is going to happen within t seconds from now, so less than or equal to t seconds from now, that's given by 1 minus e to the minus lambda times t. where lambda is the rate, say, per second. Okay. So t is the number of the amount of time. So lambda is the average number of arrivals per unit time, and so 1 over lambda is the average time between arrivals. So here are some examples. The time until we have our next car accident. This is exponentially distributed. So you figure you're going to have car accidents occur with a certain average rate, and a car accident could happen at any time, independent of other car. That's not entirely true, but let's just say independent of other car accidents. So the time until we have our next car accident, this is going to be exponentially distributed. The time until we get our next phone call, the time to the next access of a web server, the time until the next request arrives at the file server, the time required for a router to service a data packet. So it's a time. So you start the stopwatch when the packet comes in, when it arrives, and you wait until it's finished processing, and that might be exponentially distributed, say. How far we have to go before we see our next roadkill on the road. So these are all exponentially distributed variables. Also, the time between successes is also exponentially distributed, because you can always start your stopwatch at the first success and then wait for the second one. Point is, it doesn't matter since these arrivals come in at any time independently. It doesn't matter when you start your stopwatch. You're going to get the same distribution. All right. So the mean of the exponential distribution is 1 over lambda. So remember, lambda is the number of successes per unit time. So 1 over lambda is the amount of time per success, the average time per success. How much the average time it takes to get a success. And so that's actually the mean of the exponential distribution. The variance is the square of that. So it's 1 over lambda squared. So these two distributions together, the Poisson distribution and the exponential distribution, give you useful tools for analyzing real-world phenomena that satisfy this Poisson process thing, like data channels, call centers, servers that take web servers that take requests, routers that take packets, and so forth. So these are useful tools for these sorts of things. All right. So consider the file server example from the previous example. We'll say that the requests are Poisson distributed, and again, same average. So the average time for a request is a quarter second. So lambda was 4 requests per second. So let's assume the time between requests is exponentially distributed. Let's find the following probabilities. What is the mean time between requests? The mean time. What mean means average. So what is that time? It's 1 over lambda. Lambda is 4. So it's 1/4. And it's in units of time. What's the time unit here? Seconds. So it's 1/4 second, and actually exactly what was given there. Okay, so this is 1/4 second. What is the average number of requests per second? Well, we already did that. It's 4. Plot the density function and distribution function for this problem. Okay. Here it is. So the green line is the cumulative function. That's the 1 minus lambda to the 1 minus e to the minus lambda t as a function of t. And the blue line is the probability density, which is not so important. But more important to look at the cumulative distribution. So the cumulative distribution, think of it this way. If requests are coming in roughly every quarter second on average, you start your stopwatch. The chances that you will have seen your request already by, say, 1 second is very close to 1. with almost certainty, you will have seen the first request come in by 1 second after you started counting. In general, if the probability is then going to, right, as time goes on from you start your stopwatch, the probability rises basically linearly until it levels out and approaches 1 eventually. So the longer you wait, the more likely it is you've seen your first request. And the slope of this line is, what is the slope of that line? It's lambda. So the quicker the rate, the more that probability is going to go up. So the slope of the line right at 0 point there is lambda. All right. What is the probability that a request arrives within 1/10 of a second from the previous request? So start your stopwatch at the previous request time and wait for 1/10 of a second, and the probability that that request comes in within 1/10 of a second is the cumulative function where you plug in t as 0.1. And so you plug in 1 minus e to the minus 4, which is lambda, times 0.1. And so you get 1 minus e to the negative 0.4, which is roughly that. So that's about 1 out of 3. So there's about a 1/3 chance that you're going to get your first request in the first 1/10 of a second. That sounds about right. Yeah. Okay. What is the probability that the inter-arrival time between 2 requests is at most 0.5? Well, start your watch at the first request and then wait for the second one. So the probability that then the probability is going to be t less than 0.5, which is the cumulative at 0.5. I don't know why that was listed twice, but anyway, okay. 1 minus e to the minus 4, just plug in 0.5 for t, and that's what you get. So half a second is bigger than 1/4 of a second, so expect this probability to be large. All right. Let's skip that. I just want to go on. That's not that important. We skip that too. Let's determine the mean and variance for this distribution. So the mean is 1 over lambda, which is 0.25 seconds. The mean, since we're measuring time, so the output, the value of this random variable is a particular amount of time. Those are the units if we're dealing with time. So the mean is also going to be in units of time. So this is going to be 0.25 seconds. Units, as we will see, are very important to keep track of. The units will often tell you whether or not you're doing the right calculation or not. Whether or not you're doing the right calculation. If the units don't balance, you know you've done something wrong. This is especially true for physical quantities like time and distance and so forth. We're going to keep track of the units and make sure we have the right units on each side of the equation. So the variance is going to be 1 over lambda squared. So you square 0.25, and you get 0.0625 square seconds. Seconds squared. So this is in units of time squared, which doesn't really have a nice interpretation physically, but there it is. All right, done with the exponential distribution. Any questions on that? Last one. Let's just take a deep breath first. Yeah. All right. Any questions about exponential distribution? You all got it right under your belts, I know. I'm joking. I'm seriously joking. All right. Normal distribution. This is your classic bell curve distribution. It's also called a Gaussian distribution after Carl Friedrich Gauss, the famous German mathematician. All right. So what is this? Well, here's what you're going to do. You're going to fix the mean and standard deviation as separate independent parameters. So when you specify a normal distribution, that distribution depends on these two external parameters, the mean and the standard deviation. The mean is the letter mu, the Greek letter mu, and the standard deviation given by the Greek letter sigma. So for every choice of mean and standard deviation, you get another normal distribution, and it's going to look like a bell curve. And these bell curves will look different. They'll be centered in different places depending on what the mean is. And some will be spiky and thin, and others will be level and flat and wide depending on what the standard deviation is. Here is the density function for a normal distribution with mean mu and standard deviation sigma. It's this fraction which is constant. It only depends on sigma, but ignore it for a second. Here's where the action is going on. It's the natural exponential. It's e to this power. It's minus 1/2 times x minus mu over sigma. Squared. Okay. So let's just look at this for a second. If x is equal to mu, what do I get? I get 0. So that whole exponent is 0. So what is e to the 0 is just 1. Okay. If x is deviating from mu, then this is positive, right? So when you square it, you're going to get, you're going to get something non-zero, so when you square it, you get something positive, right? But now you multiply it by negative 1/2, so that's going to be less than 0. That's going to be negative. So if you take e to a negative number, what's it going to be? It's going to be less than 1. And in fact, the further away you get from the mean, this number is going to go down exponentially. In fact, really fast. So that gives you your typical bell curve shape. Right at the mean, let's say this one. So the mean here, it says the mean is 4, but the picture doesn't really, it looks like the mean is actually 5 given the picture. I think that's a misprint. So let's say the mean is 5, not 4. And the standard deviation is 2. Well, the point is the mean is going to give you the maximum value. It's right at the tip. It's centered over the 5. That's the mean. And then it goes down symmetrically on both sides exponentially because it doesn't matter which direction you're going from the mean. Once you square it, you're going to get the same value. So this goes down very quickly on each side. And the rate at which it goes down is also controlled by the standard deviation. So if you have a large standard deviation, you're dividing this by a large number, which means you're not going to go down as quickly. If you have a small deviation, you're going to shoot right down quick. Okay? So small sigma gives you a thin, spiky bell curve. And large sigma gives you a spread out, diffuse bell curve, like that. A more gentle bell curve. All right, so here's where sigma equals 2. What's the point of that constant there? The constant there, is just to normalize things. When you integrate when you integrate this thing from minus infinity to plus infinity, you have to get 1. And that's why that thing is there, because if you just integrate this exponential, you don't get 1. You get actually sigma times the square root of 2 pi. So you have to divide by sigma times the square root of 2 pi to get things so you get exactly 1 when you integrate this whole thing from, when you integrate, you take the entire area under the bell curve, it has to equal 1 from minus infinity to plus infinity. Okay. Questions about the general setup. So we've got a nice formula for the density function. And, of course, the cumulative distribution function just integrates the density from minus infinity up to the point x in question. There's no nice closed form for this, unfortunately. Okay? That's kind of rotten, but there isn't any. But the way we're going to actually get these is by table lookup. So in the back of the book, I think is Appendix D. I think it's right in the back. Maybe just right before the index. Yeah, what page is that?
That is page 597, sir.
Yeah, 597 and 598. Especially 598. 597 is just the explanation. But page 598 actually gives you a table of values for normal distribution. But for a particular normal distribution. The normal distribution where the mean is 0 and the standard deviation is 1. So it doesn't give you all possible normal distribution. It just gives you this one. We call this the standard normal distribution. Or the normal distribution in standard position, where the mean is centered at 0. So mu is equal to 0, and the standard deviation is just 1. That's the simplest positive standard deviation you can have. And so here it is. This is this standard normal distribution. The book gives you the cumulative function for this distribution for lots and lots of different values of x. So what it's giving you, I can't draw on the board there. What it's giving you, if you take a value of x like 2, it's giving you the entire area under the curve from minus infinity up to 2. Okay? Now notice look at the table and notice where does the table start? What x value does the table start at? Starts at 0. Yeah. So it actually only gives you the values from 0 on up. It doesn't give you the negative values. How do you get the negative values?
Minus.
Yeah, 1 minus. So that's worth actually drawing. So here's the standard normal distribution. Okay. So you've got an entry for some x here, like 1.5. But you really want to find it for minus 1.5. So here's what you want. You want, what is that area? Well, here you use the fact that this bell curve is symmetric on both sides of 0. So it's symmetric with reflection in the y-axis. So this area is the same as this area, right? Same area. To the same shape and everything. Okay? So, how do you find this area? Well, the whole area from minus infinity to plus infinity is 1. That's the normality condition. So what's this area? It's going to be 1 minus that area, from minus infinity up to x. So this area is going to be 1 minus the cumulative distribution function, which I'll call capital Phi. of x. So that's this area, which is also that area. So this is equal to phi of minus x. So if you want to find phi of a negative number, you go and you find it for the positive number, and then take that number, subtract it from 1. And that tells you how to do it for the negative number. So what that effectively does is it extends the table into negative territory as well, by this simple way of doing it. So questions on table lookup. Okay? So if I ask for the standard normal distribution at minus 2.5, you could just look up in the table. So the columns give you, I think, in increments of 1/10, and within each row, I'm sorry, the rows give you increments of 1/10, and within each row you go up in hundredths, from 0 hundredth up to 9 hundredths. Okay, I think that's how that works. Haven't seen the table in a while. Oh, it's
slide 44.
Okay, awesome. Okay. Well, I wanted to do this first because now we have our next problem is what if your normal distribution is not standard? What if it's somewhere else? So mu is 4 here and sigma is 2. Can we use the table for the standard distribution to get the cumulative function for a non-standard distribution? So that's the question. And the answer, of course, is yes. And it's going to be easy. All we have to do is convert from one scale, which is the x scale, to the standard scale, which we'll call the z scale. And that conversion works as follows. If you think of the normal distribution as being a function of z, so maybe I should have called this z. So this is the z-axis, if you like. Then, if you want to find, say, the cumulative distribution at some point x for any old Gaussian distribution anywhere, you convert to the equivalent z value and look that up in the table. So your z value is going to be x minus the mean divided by the standard deviation. So the idea is to find the cumulative function, say, here at x equals 7. You take 7 minus 4, which is the mean, so that's 3, divided by 2, that's 1.5. Go look up in the table at 1.5. Does that make sense? All right. That's the general approach, how we're going to do this. So let's do it. Let's actually do it. Let's do an example. Okay. See if we can get it. All right. Awesome. So let Z denote, but keep your books open. Let Z denote a standard normal distribution. So Z is just mean 0, standard deviation 1. Find the following using the table providing class. Probability that Z is at most 2. So what is that?
97725.
97725. Yeah, so you just look up Z equals 2. Okay? The probability that Z is bigger than 1.5. So just using complementarity, P that Z is bigger than 1.5, that's the complement of the event that it is less than or equal to 1.5. So this is 1 minus the probability that Z is less than or equal to 1.5. So now that's 5. So what's that? So what's 5, 1.5? 9.33. So subtract that from 1, and what do you get? You get something small. Okay. You don't have to do it. Right, does that make sense? So you could use the cumulative function to get other things besides less than or equal here. How about Z is less than or equal to minus 2? Well, now you're in negative territory, so you apply phi to 2 and then subtract that from 1. So what's that?
0.97725 is for
Okay, and then subtract that from 1, and you get, again, something small.
0.133.
Yeah, that sounds about right. 1.0. 0.0228. Okay, sound good. Let's do D. D is useful. The probability that Z is between 0 and 1.73. Ooh. Now I've got 2 constraints. Now I'm interested in, what am I interested in? Can I get by? No. I'll redraw this. So it's in between 0 and 1.73, and that's going to be about right there. So now I'm interested in that area. Right? So the area between 0 and 1.73. So how do I get that?
Look it up for 1.73 and then subtract 0.5 because you know that's what 0 is.
Right. So to get this, you look it up, you get the cumulative function from minus infinity to 1.73 and subtract off the cumulative function from minus infinity to 0. So this is going to equal phi of 1.73 minus phi of 0. And in general, this works for any two limits of an interval. You take the cumulative one for the right and subtract off the cumulative one for the left. So what is this? So this is 0.5, right? Because it's right in the middle. So it's exactly half. So what's this going to be?
0.95818.
0.95818 minus 0.5, so that's going to be 0.45. Right. Okay. How about that one?
So take the value for 1,
Yeah.
subtract the 0.5 for 0, and then multiply that times 2 since it's equal on both sides.
Oh, I see. It's equal on both sides. So, okay. So you take the thing for 1 minus a half, and that gives you from 0 to 1. And then take that times 2, and that'll give you the same piece on the other side. Good. That'll work. So another way you could do it is you could take 1 minus phi of minus 1, right? You do it that way as well, and then just convert this back. So this is 1 minus phi of 1. And that's 2 phi of 1 minus 1, which is 2 times phi of 1 minus a half, which is exactly how you did it. So it's the same. So good. Either way. Did I do that too quick? Probably. No? Okay.
So here we go.
All right. So final example, and then we'll call it a day. So the percent of errors received using a particular data channel is normally distributed with a mean of 2% and a standard deviation of 0.3%. What is the probability that the percent of errors does not exceed 2%, does not exceed 3%? Okay. Let's agree on our units. Our units are going to be percents. So 1 means 1%. Okay. So we can ignore the percent sign and say the mean is going to be 2. and the standard deviation is 0.03. So what is the probability the error does not exceed 2%? Well, now, this is a non-standard distribution, so we convert it into the standard distribution using our formula here, which is z is x minus mu over sigma. That's x minus 2% divided by 0.3%. So the probability that x is less than or equal to 2 is the same as the probability that z is less than or equal to what we get up here, which is 2 minus 2 over 0.03. Well, that happens to be 0. So the probability that x is less than or equal to 2 is the same as the probability that z is less than or equal to 0, which is the cumulative function at 0, which is, we know, is 0.5. So it's always a 50-50 chance that you're less than the mean. All right. How about 3? Well, now we plug in x equals 3, and we get 1 over 0.3, which is about 3 1/3. So now we go and look up at 3.33, roughly, and we get roughly 9.9996. So with very high probability, well, here, how many standard deviations are you away from the mean at this point? The mean is 2%. Standard deviation is 0.3. 3%, that's more than 3 standard deviations away. So actually 2 standard deviations away is already, probability is already pretty close to 1. 3 standard deviations away, it's even much more close to 1. Okay. We're really counting the number of standard deviations because you divide by the standard deviation. All right, I guess that's my last slide. Yay. All right. One more thing. Let me ask. Does anyone just know? Suppose you look at a bell curve like this. Somebody shows you a bell curve. Do you know how to find its standard deviation just by looking at it? Do you know this? Not quite a half.
You look at where it approaches 0 and divide that by 2 on the x-axis?
Well, where does it approach? It approaches 0, off at infinity. So, yeah, that doesn't help.
It has to be something related to a peak.
It's related to the shape of the curve. Notice the curve is concave down. And then it hits an inflection point, and then it's concave up. So right where it switches direction, right this inflection point, that distance, that's the standard deviation. So look to see where the curve inflects. And that tells you what the standard deviation is actually. I don't know when you'd ever use that, but if you saw it in a book, then you can kind of guess what it is. All right, that's all I got. Any questions on anything? All right. So you know the drill. See you at 1:30 and 1:30.